A 150-kilometer-per-hour Martian storm hits you with the force of a gentle Earth breeze. That sentence sounds like an exaggeration. It is not. Picture a colonist standing on the surface, drink in hand, watching the horizon darken. A wall of dust rises in the distance, towering, racing toward them. A speed that would flatten sheds and snap power lines back on Earth. Every Earth-trained instinct says, brace for impact. The storm arrives. It wraps around them in a haze of red-brown dust. Nothing happens. The drink does not spill. Their stance does not shift. The visual apocalypse rolling across the landscape carries less physical force than a lazy afternoon breeze on a beach. Hollywood taught you to expect the opposite. For decades, disaster fiction set on Mars has leaned on one assumption without ever questioning it. Bigger wind number, bigger danger, exactly like a hurricane advisory back home. The most famous version of this myth comes from The Martian. Its opening sequence shows a massive windstorm violent enough to flip a spacecraft, debris hurled hard enough to impale the protagonist. It is a gripping scene. It is also, by the film's own admission, wrong. Wind force is not just about speed. That is the part intuition skips. Every weather forecast on Earth trains you to think in one variable. A stronger wind is a faster wind, full stop. And the number in kilometers per hour is treated as a complete description of danger. That shortcut is not wrong on Earth. It is just incomplete. And the missing piece never shows up because Earth never varies enough to expose it. Force comes from kinetic energy, and kinetic energy depends on both speed and mass. The dynamic pressure wind actually exerts on a surface scales with air density multiplied by velocity squared. Speed matters. Mass matters just as much, maybe more. On Earth, you never notice mass is a variable because Earth's atmospheric density barely changes wherever you go. Sea level, a mountain pass, a coastal cliff. The differences are real, but small enough that speed alone still predicts danger reliably almost everywhere a person is likely to stand. A 100-kilometer-per-hour wind at a beach and a 100-kilometer-per-hour wind on a hillside feel close enough to identical that nobody bothers separating the two variables in casual conversation. Mars breaks the shortcut completely. Because the density difference is not a rounding error, it is not the kind of DAP you could ignore and still get a roughly correct answer. It is closer to 2 orders of magnitude, a gap so large that no amount of speed increase on Mars's side can climb back over it. Mars's atmosphere is roughly 100 times less dense than Earth's. At the surface, Martian air weighs in around 0.02 kilograms per cubic meter. Earth's sits near 1.2. That is not a small gap. It means a cubic meter of Martian air moving at any given speed carries a tiny fraction of the mass. The same volume of Earth air would carry far more. Martian dust storms can reach wind speeds up to 150 kilometers per hour during major regional and global events. That figure gets repeated constantly in casual descriptions of Mars weather, almost always without the second number that actually determines danger. Speed without density is half an equation dressed up as a whole one. That number alone sounds like a serious hurricane, roughly Category 4 territory back home. But run that speed through the density gap, the actual dynamic pressure collapses to something comparable to a 10 to 15 km/h breeze on Earth. Noticeable, maybe enough to feel through a suit, nor close to knocking anyone down. Here is the part that makes the mismatch worse, not better, for anyone hoping the physics would at least partially cooperate with the cinematic version. It would be one thing if Mars's thin air simply meant weaker wind at the same speed as Earth's. It is another thing entirely that even the compensating speed boost Mars gets from lower atmospheric friction cannot begin to close the gap. Dynamic pressure scales with velocity squared, so doubling wind speed should quadruple its force. Mars does get somewhat faster storms than Earth, thanks to lower friction and that thin air. But the density reduction is a factor of 60 to 100. The speed increase Mars offers is at most 2 to 3 times a typical Earth storm. The math does not come close to balancing. 3 ordinary comparisons make the missing variable easy to feel instead of just calculate. A leaf blower running at hurricane speed is still just air, and everyone who has ever held one already knows this instinctively without needing a formula. It moves fast. It moves almost nothing of substance behind that speed. Compare that to a fire hose moving at the exact same nozzle speed. The fire hose will knock you flat. The leaf blower barely musses your hair. Or think of two boxing gloves thrown at identical speed, one packed with feathers, the other with sand. Watch both gloves in slow motion, and you would see identical arcs, identical swing mechanics, identical timing all the way to contact. The feather glove barely registers as a hit. Same velocity, same swing, but almost no mass means almost no force delivered on impact. Mars's wind is the feather glove, moving at a speed that looks, on paper, like sand. There's a crowd version of this too, and it is the one that scales most naturally to something as vast as a planet-wide storm. Picture a dense crowd of people walking slowly into you versus a handful of sprinters covering the same ground in the same time. The slow, dense crowd shoves you back harder. The fast, sparse group barely nudges you. Total mass in motion beats raw speed almost every time. None of this is a criticism of the movie's craftsmanship. Andy Weir, who wrote the novel The Martian, has said in interviews that he knew the storm's force was scientifically wrong. He used it anyway, deliberately, because the plot needed a triggering disaster, and the wind made a dramatically clean one. It is the single acknowledged exception inside a book otherwise built on careful, rigorous science. One exception made on purpose for one scene. The rest of the book earned its reputation honestly. Weir researched orbital transfer windows, potato-growing chemistry, and the exact atmospheric composition a colonist would need to survive, all with obsessive accuracy. The storm was the one place he let drama win. So, if the wind cannot hurt you, what actually threatens a real Mars mission during a storm like this? The answer flips the entire threat model on its head, trading a dramatic mechanism for a quiet one. The real danger has nothing to do with mechanical force. It has everything to do with what the dust itself does once it becomes airborne. Fine Martian dust particles are electrostatically active, clinging to surfaces the way packing peanuts cling to a sweater. That dust settles onto solar panels. It blocks sunlight. It starves power systems slowly, silently, without a single dramatic gust involved. This is not a hypothetical risk. It already ended a mission. In June 2018, NASA's Opportunity rover, working in Perseverance Valley, went silent after a planet-encircling dust storm blocked sunlight to its solar panels for months. It was one of the most severe global dust events ever recorded on Mars. Mission controllers eventually confirmed the cause. Not wind, not structural damage, insufficient power from blocked sunlight, plain and simple. 15 years of operation ended by dust settling quietly on glass. Engineers watched the rover's signal fade, not because anything broke, snapped, or toppled, but because the panels simply stopped receiving enough sunlight to charge the batteries. No collision, no damage report, just darkness spreading slowly across the sky above Perseverance Valley until there was no longer enough light left to work with. Solar power loss is the slow half of the danger. There is a faster, sharper half riding alongside it. The dust carries a second hazard beyond blocking light. Storm friction charges the particles with static electricity, the same basic effect that makes a balloon stick to a wall after rubbing it on your hair, just scaled up across an entire dust cloud. That static creates real risk for exposed electronics, capable of discharging into sensitive equipment. It is a threat with zero overlap with wind force, requiring completely different engineering, grounding, shielding, careful material choices, not thicker hulls. Real mission planning reflects this correctly, even where fiction does not. NASA's design reviews for surface hardware do not include structural wind resistance testing rated for anything close to hurricane force impact, because that testing would be solving a problem Mars does not actually present. The single most visually terrifying phenomenon on Mars turns out to be almost harmless in the way people fear it. Genuinely dangerous, though, in a way almost nobody pictures. A wall of dust can grow large enough to engulf the entire planet. It can block sunlight for weeks and end a 15-year mission. yet it poses essentially zero risk of physically pushing a person over. That is the twist worth sitting with. The scary-looking threat is nearly toothless. The quiet, boring-looking threat is the one that actually kills missions. None of this makes The Martian a bad film, or a badly researched one. If anything, it makes the choice more interesting, not less. A storyteller who has done the math on almost everything else in a story, and then knowingly bends one single fact for pacing, is not sloppy. That is closer to a magician telling you which trick they are about to perform before they perform it. The myth persists anyway, because a howling wall of dust makes better cinema than a slow film of grime settling on a solar panel. Drama rewards force you can see. Real Martian danger rewards patience you cannot. There is a broader principle buried inside this one storm, and it outlives the specific numbers. Force is never just speed, it is mass times acceleration, and any intuition that quietly assumes a fixed Earth-like density will misfire the moment it meets an atmosphere that does not match Earth's. That assumption would fail identically on Titan or on any hypothetical world whose air behaves nothing like the air humans evolved breathing. On Mars, that missing mass is the whole story. Once you notice it, you can never watch a Martian dust storm on screen the same way again.